This week we're going to continue our discussion of limits. For the first part, we're going to do several limit computations. We're going to see ways we can use algebra to compute the limits, and then we're going to see one application of limits. Now first, we'll start with the algebraic limit laws. Well, first, you might notice this is a whiteboard now. It's no longer a chalkboard. We'll see how the whiteboard works. I have both options here. The algebraic limit laws. Now, last week we saw a couple of these. We saw the first two by using graphs. But let's discuss all of them. Let f and g be functions of x, and let c be a constant. Then we have 7 parts. First, limit as x goes to a. So a can just be anything in our on the x-axis, anything in the domain. Limit as x goes to a of a constant is that constant. We saw that result with a graph of a horizontal line last week. The second one, limit as x goes to a of just x, is a. We saw that with the graph of the function y equals x last week. The other 5 we did not see, and we'll see this week how we use these. The third and fourth, very important. The third one says the limit as x approaches a of a sum of functions or a difference of functions is given by the sum or difference of their limits. So limit of function plus another function, you can break that into 2 limits and do them one at a time. If you start with 2 things added together, you add them. You start with 2 things subtracted, you subtract them. Rule 4, limit as x goes to a of a constant times f is the constant times the limit. So here, if we have a number in front of our function, and we're doing the limit, we can pull this number out front and then do the limit. A very useful and very important rule throughout calculus 1, 2, and 3. Using rule 4 all the time throughout calculus simplifies a lot of what we're doing. Well, it doesn't simplify it a lot. It makes it easier to not get overly distracted by the numbers in the problem. And we'll see in calculus the numbers matter much less than the variables. Rule 5, the limit of a product. So here we have f times g. Well, the limit of the product, you can do the limit of the first one and then multiply it by the limit of the second one. Rule 6, limit of a quotient, is similar. You can do the limit of a quotient by doing the limit on top and dividing by the limit on the bottom. And of course, that works only if the bottom is not 0. So you can't divide by 0. And rule 7, limit of a function raised to some power, is the limit, all raised to some power. So now let's look at examples of how all of these rules are used. So first, let's do this one. Find this limit. Limit as x approaches 2 of x squared minus 5x plus 3. Now, those of you who may have seen calculus before know a minor shortcut. Those of you who have not seen calculus before will have to wait about 10 minutes for the minor shortcut. Here, all we have are those 7 limit laws. Well, what do we have here? We have something with x's, something else with x's, and a number. But we have 3 functions added together. And that's a subtraction, but we have 3 things added together. So we can break this apart using limit rule 3. hand does not erase a whiteboard as well as it erases chalk. So let's use rule 3 equals, and I'll say by rule 3. We're going to break this into 3 parts. Well, rule 3 says we can do that. Notice we took the negative out because we have x squared minus 5x. So using rule 3, we split that into 3 limits. Well, now we have 3 limits, but so you might expect that doing 3 limits is not easier than doing 1 limit. But we have other rules at our disposal. For example, here we have a function raised to the 2nd power. Well, we can use rule 7 with n equals 2 to turn this into this function, or to this limit. This limit on the inside of the parentheses we know how to do using rule 1 or rule 2. Which rule is it? Using rule 2. And we'll get there. But first we'll deal with this. We have 5x. Rule number 4 says we can take that 5 out front. And then just do the limit of x, as long as we remember to multiply by that 5 and that negative. Here we have the limit as x approaches 2 of 3. Well, 3 is a constant, so we can use rule 1 on that and conclude that that limit is 3. So we use rule 7, rule 4, and rule 1. So let's write that down. 7, rule 4, and rule 1. Well, now we just have to compute this limit and this limit. Well, both of them we can use rule 2 on. So equals by rule 2. The limit as x approaches 2 of x is just 2. And we still have to square it. Minus 5 times the limit as x approaches 2 of x, which is 2. That's a multiplication. And then still plus 3. Well, now you just have to combine these numbers. What? 4, negative 10, and 3. So that gives you negative 3. So here we used several limit laws to split this polynomial up. Well, to split the limit of this polynomial into more limits. And yes, that is the number I have in my notes. Let's do another example. Let's do this example. Let's do limit as x approaches not 2 this time. Let's have x approach negative 3 of root x plus 4 times x squared minus 2. Well, here we have a product inside our limit. So we can split that using the rule that that has a product inside the limit. Which rule number is that? That's rule 5. Rule 5 says the limit of a product can be broken into the limit of one times the limit of the other. I guess I'll put this L on the other side of this. No, let's just rewrite that. Times, I'll put her over here. Times limit as x approaches negative 3 of the other thing. Well, now we have to do these two limits. Well, the first one, remember, a square root is just an exponent of 1/2. So we can rewrite this by taking the square root outside of the limit. Now over here, we have a difference. So we can do that by splitting it into the difference of the limits. And in that, in doing this, we use what? Rule 7 to bring that exponent out. We used Rule 3 to split that into the limit of the differences, or the difference of the limits. Well, now what can we do? Well, here we have the limit of a sum. So again, we can use Rule 3. Here, this limit was similar to in the first example, and we did that by doing Rule 7 on that, and then Rule 2. Here, we have the limit of a constant, so we can use Rule 1 on that. So let's do all of that. First, we want to split this into the sum of the limits. That exponent 1/2 is still there. All we did was use Rule 3 to split this into two limits. Well, now we need to multiply by this. So this one we would use Rule 7 on to bring that exponent out. And here we know this limit from Rule 1. That limit is just 2. Because 2 is a constant. And what rules did we use here? We used 3 on this part, and we used Rule 7, and we used Rule 1. So 3, 7, and 1. Well, now all we have to do is use Rule 1 on this, and use Rule 2 on both of these things, and then put all the numbers together. So by Rules 2 and 1, this limit is just -3 by Rule 2. This limit is 4 by Rule 1. This limit is -3 by Rule 2. So let's write that down. So we have -3 plus 4, all of the 1/2, times -3 minus 2. And what does that equal? Well, that's 1 to the 1/2. 1 to the 1/2 is 1. -5, 1 times -5 gives you -5. Oh, that is not the same as what I wrote here because I made a mistake in this last step. What did I do? Well, I forgot that square. Good thing I had the answer written on paper in front of me. So this was still -3, 4. I just forgot that square. So we have -3 squared. Hopefully, if you were watching the video, you caught that before I caught that. So now we have still 1 to the 1/2, which is 1, and here we have 9 minus 2, which is 7. So we have 1 times 7, which is 7. And that is what I have here. Now, take a look at these last two examples. I didn't do one with a quotient. A quotient would follow very similarly to this first step here when we split the product. It would be the same with a quotient, and then you'd go through similar steps to this. But notice what we did here. All of these steps told us we could eventually substitute whatever this number is for x. And you can see what happens, or you might ask yourself, what happens if you substitute this number for x up here? Well, try that. -3 plus 4, all to the 1/2, times -3 squared minus 2. Well, that's what we have down here. -3 plus 4 to the 1/2, times -3 squared minus 2. In the previous example with that x squared minus 5x plus 3, the same type of reasoning worked. These algebraic limit laws allow us to use algebra to compute limits. And in particular, they allow us to substitute the numbers we want. So in general, you don't have to go through all of these steps explaining the limit laws when you can just do a substitution. Now, when can you do a substitution? Well, a lot of the times you can. Some of the times you can't, but you can interpret a substitution. And we'll see that today. Now, this theorem does not show up in the textbook written in this form, but I think writing it like this provides a pretty good summary of several results using limits. So here, for general f and g, upon direct substitution, the limit of this quotient, so limit of some fraction with functions, we'll just say a fraction with functions now, the limit takes one of the following forms upon direct substitution. One, you could get a 0 on top and a number on the bottom. Here, that pound symbol will be a non-zero number. Positive or negative, just non-zero. This symbol 0 will be for a 0 number. So upon direct substitution, you could get 0 over a number. You could get number over a number. You could get 0 over 0, or you could get a non-zero number over 0. Now, in these first two cases, well, 0 over a number, that's a fraction that reduces to 0. 0 over a non-zero number. Here, number over number, that's another fraction. In either of these cases, this simplified fraction is the limit as a result of the algebraic limit laws. If you wind up doing a direct substitution and getting 0 over 0, we'll have to do algebra. And the algebra will allow what's causing the 0 over 0 to go away. And once that happens, might have to do it more than one time. Once that happens, you can reduce the problem to case 1 or 2, and then the simplified fraction upon direct substitution is the limit. Now, 4, you could get a number over 0. And in this one, what we will do is check what happens on both sides of A and analyze. Now, on one side of A, it's going to be a positive or a negative infinity. On the other side of A, it's also going to be a positive or a negative infinity. So we'll see what we mean by that once we start doing some examples with case 4. So let's do several limit examples. Example. Compute the limit. Limit as x goes to -3 of x plus 3 over x minus 3. Let's do that one. We're going to go over instead of down this time. Let's do 2 examples. Limit as x goes to +3 of 4x squared -3x positive 2 over x and a -7. Now, this theorem in its statement says it's a fraction. The first example we did before with, I forget the numbers, 4x squared. I forget the numbers. The first example we did today was just a polynomial. This applies to polynomials as well, because g of x could just be 1. So writing it as a fraction is just a convenience, because it provides a more general theorem than if we just use polynomials. So right here we have these 2 limits. When you do these limits, the first thing you should hope works is a direct substitution. You should always try direct substitution first, because if you do a direct substitution and get a number, you're done. And it's nice to be done with problems, because then you can move on to the next one. So let's try a direct substitution here. Direct substitute on top, you get 0. On bottom, you get -6. Well, that's 0 over -6. That's case 1, because that's a fraction which reduces to 0. So that limit is 0. That is case 1. I'm not going to write case 1. It is case 1. You can write that in your notes if you want. I'm not going to write it on the board. Let's try this next one. The next one, again, let's hope direct substitution works. Well, with direct substitution, what do we get? 4 times 9 minus another 9 plus 2. Okay, that's some number on top. What do we got on the bottom? 3 and negative 4. No, not 3 and negative 4. 3 and negative 7, which makes negative 4. Well, what's that number on top? The number on top, 36, 38, negative 9. 38 and negative 9 makes 29. The bottom is negative 4. So we have a number over a number. So this number is our limit. This first one was an example of case 1, where we had 0 over a number. This next one was an example of case 2, where we had number over a number. Let's do a couple other examples. Let's do 3 examples. I guess I'll tell you now. These next 3 examples will be case 3. Now, the case 3 rules said, what? Do algebra until the 0 over 0 goes away. These 3 examples will illustrate 3 different types of algebra, or 3 different ways we could use algebra to cancel a 0 over 0. Let's do this one first. Limit as x goes to 2 of x squared minus x minus 6 over x, not minus 6, sorry, that should be a minus 2 on top. Now on the bottom, x squared plus x minus 6. Well, here, again, you should hope direct substitution works. What happens with direct substitution? Well, you get what? 4 minus 2 on top. On the bottom, you get 4 plus 2 minus 6. That's 0 over 0. 0 over 0 is not a number. So we are in case 3, so we're going to have to do some algebra. Now right here, the algebra we can do is by factoring these 2 polynomials. Both of them do factor. What do we need? Numbers that multiply to negative 2 add to negative 1? Well, 2 and 1 do that. On the bottom, we need numbers that make 6 and make 1. 2 and 3 make 6. 2 and 3 make 1. And we needed 1 to be negative. One of them to be negative. So now we wrote this in this form. And you'll notice the x minus 2 shows up on the top and the bottom. So this fraction reduces to just, or this limit reduces to just this limit. Well, now you hope that you can do a direct substitution. Now, if you do direct substitution and get 0 over 0 again, you'll have to do more algebra. But here, when you do direct substitution, what do you get? 2 plus 1 over 2 plus 3. So that is number over number. So that is the limit. That's one type of problem where you could arrive at 0, 0, where you could arrive at a 0 over 0 upon direct substitution. With that one, we used factoring to get rid of the 0 over 0 term. Let's do another. let's do this limit now. So what do we have here? Limit x goes to -4 of this. Again, your first hope should be that substitution works. You try substituting, you get what? √9 minus 3. So that's 0 over -4 plus 4. So you get a 0 over 0. So you have to do some algebra. Here, we're not going to immediately factor this. Well, we're not going to factor it at all. What we're going to do is multiply by a convenient 1. Now, before we do that, let me make one remark on the side. And we'll use this in this problem. I'm not just writing this for fun. I'm writing it because it's useful. Right here, we have the rule where the difference of squares factors into the one thing plus the other times the one thing minus the other. Well, we're going to use that to figure out what to multiply by. Square roots are not convenient algebraically. So it would be nice if we could get rid of that. Well, I will tell you that this will get rid of it. Now, why does this get rid of it? Well, first of all, we're allowed to do this because we're just multiplying by 1. Multiplying by 1 doesn't change anything. Well, it doesn't change the problem. It allows us to still use equals. But what happens in the numerator? What happens in the numerator? Well, we have something minus something times that same first thing plus that second thing. That's the same as this difference of squares breakdown. Well, maybe it's not directly the same. Let's change the plus and the minus around. There. Now that numerator is in this form. So if we simplify the numerator, we just do the first thing squared minus the second thing squared. Well, a square root and a square cancel each other out. So the first thing squared is just x plus 13. There's a squared. The next thing, b, is 3. 3 squared is 9. So the numerator simplifies to just that. Now, what happens to the denominator? Well, you could you could multiply out that denominator, but we are going to see that doing that is not necessary. So we're just going to write it as the one thing times the other thing. Now, the reason it's not necessary is because we know eventually we're going to have to cancel out something that's causing a 0 over 0. Well, right here, this x plus 4 is causing the 0 in the denominator. So let's see what happens next. Well, we have a 13 and a -9 on top. You can combine those and get a 4. Combine 13 and 9 on top and make 4. And now you'll notice the top and the bottom both have an x plus 4. So we can cancel those out. That divided by that reduces to 1. So there's just a 1 on top. There's an x plus 13 under a square root and a positive 3 on the bottom. We're taking the limit as x goes to -4. We hope all that algebra we went through allows us to just do a direct substitution. And what happens on a direct substitution? Well, you get a 1 on top. You get a square root of 9, which is 3. And another positive 3 on the bottom. So that makes 1/6. And that is the number I have here. So notice in this one, what we did when we had this square root was multiply by a convenient 1. We used the difference of squares on top. We left the bottom alone. And then we simplified the top, and that allowed us to cancel out an x plus 4. And then we were able to do a direct substitution. Let's do another. Let's do this limit. Limit as x goes to 1 of 1 over x plus 1 minus 1 over 2 over x minus 1. So here we have a 3-tiered fraction. Whenever I have to deal with a 3-tiered fraction, I usually like exaggerating the overall fraction bar. Because in general, when we're thinking of fractions, we want to think of things on top, things on bottom. And having an extra large overall fraction bar allows me to organize the top and the bottom. While we have this limit, let's try direct substitution. Direct substitution gives 1 over 2 minus 1 over 2. Half minus a half is 0. So that gives us 0 on top. On the bottom, you get 1 minus 1, which is 0. So you get a 0 over 0 again. Well, we have a 0 over 0. We're going to have to do some algebra. What kind of algebra can we do here? Well, we have all these fractions. Let's try combining them. Well, in this combination, we're going to leave that denominator alone for now. Let's just work on the top, because the top has lots of fractions. Well, we'll see how far across we have to go. The common denominator on top is 2 times x plus 1. Common denominator on top, 2 times x plus 1. Here, we need another 2. Here, we have a negative sign. Here, we need an x plus 1. So here we have a 2 times 1, giving us that 2. Here we have an x plus 1 times that 1. So the numerator simplifies to that. I guess I didn't need to draw this all the way over here. The denominator for now we're going to leave alone as x minus 1. Well, what can we do with this now? Well, we have 2 minus x plus 1. We can simplify that a little. So up here we have 2 minus x minus 1. 2 minus x minus 1. 2 and negative 1 make just a positive 1. So we have 1 minus x over 2 times x plus 1 over x minus 1. Now right here, it's not immediate whether we've canceled enough, but you'll notice if you do a direct substitution again, you get a 0 on top. You get 0 over 4, so that's 0 on top over 0 on the bottom. So we've not done enough algebra to allow us to do a direct substitution. So let's now get rid of this 3-tiered fraction and replace it with a 2-tiered fraction. Well, how can we do that? Well, we have this thing divided by this thing. as a side note, 5 divided by 2 is the same as 5 times a half. Dividing by something is the same as multiplying it by its reciprocal. So let's do that here. So we have this fraction divided by x minus 1. That's the same as this fraction times 1 over x minus 1. So that just throws another x minus 1 in that denominator. Well, what can we do here? If we tried substituting, we'd still get a 0 over 0. But we'll notice this term up here causing the 0 looks a lot like this term down here that's causing the 0. How do these two terms differ? Well, this one has a positive x and a negative 1. This one has a negative x and a positive 1. We can make them look the same by removing a negative from one of them. I will remove the negative from the top term. So removing a negative from the top term makes it clear that there's an x minus 1 on top and an x minus 1 on the bottom. So just rewriting that gives us that this is the limit negative 1 over 2 times x plus 1. And now we can do a direct substitution. We get negative 1 over 2 times 2, which gives us negative 1/4. That's a 4 on the bottom. I don't know if that looks like a 4 on camera. It doesn't look like a 4 that clearly in front of me. There. So here we combined all these fractions until we were able to cancel the x minus 1. And those are the, in general, those are the types of case 3 problems we could see, the 0 over 0 cases. Let's now consider case 4. And before doing an example of case 4, let's make one observation. Because these case 4 limits will share some similar properties. Let's first look at, well, let's remember case 4 is number over 0. Case 4 is a number over 0. What's the most basic number over 0 you can think of? Well, if number is 1 and 0 is 0. 1 over 0. What does 1 over 0 look like? Well, we don't know what 1 over 0 looks like because we don't, division by 0 is not a well-defined operation. But we've seen things that are like 1 over 0 before. In particular, let's take a look at this graph. 1 over x. Now the graph 1 over x is not defined at 0. But what happens close to 0? Well, first of all, what happens on both sides of 0 is not the same. But we can make this observation. On the right side of 0, so on this side of 0, as you get closer to 0, this function goes up higher and higher without end. Well, we can translate that into limits. The symbol we use for a quantity which gets higher and higher without end is infinity. So on the right side of 0, the limit of 1 over x is infinity. And it's a positive infinity because it's going larger than any finite number. Now what happens on the other side of 0? Well, on the other side of 0, as you approach 0, this goes lower and lower. It never hits 0. It gets lower and lower. It gets smaller than every number. The symbol in math we use for a quantity which gets smaller than any number is negative infinity. So let's write this as an observation. Observe these two limits based on that graph. Well, and consequently, we know that the limit as x approaches 0 doesn't exist because these aren't the same. But these limits of the form number over 0 might look like this. They could also, I'm not going to write these limits out, but they could also look like this. Maybe I will write these limits out. Let's look at this graph. So I will write these limits out. In this graph, on the left of 0, let's do the right of 0 since that's what I did first over there. On the right of 0, still, this piece goes larger than any number. So the limit as x goes to 0 on the right of this function is positive infinity. But on the left of 0, you'll notice it also keeps going up, gets larger than any finite number. So on the left of 0, the limit of 1 over x squared is also positive infinity. And with this, we'll conclude that theorem that said limit, the last thing we did last week, said limit on the left equals limit on the right if and only if the limit is that number. That worked when L was a real number. We were using L as a real number. We will extend that to positive and negative infinity. In other words, we will use similar reasoning to conclude that this limit as x goes to 0 of 1 over x squared is positive infinity. And with positive infinity, you don't always have to write the positive. Just like with numbers, if you don't write a positive, it's assumed you mean positive. Now, in the 1 over x example, we couldn't reach this conclusion because we had different things happening on both sides of 0. But for 1 over x squared, we had the same thing happening, so we will conclude from that that the limit is that infinity. Now, with these observations, well, these observations, in a sense, are the most general types of number over 0 limits. And all limits that are number over 0 are going to behave similarly to this example or the 1 over x example. And what we have to do is look at both sides of the problem number, meaning the limit as x goes to a. So both sides of a, that is the letter I used before. Check both sides of a to see if it's positive infinity, as it is here, or negative infinity and positive infinity, as it was in 1 over x, or it could be both negative infinity if we flip this around. So let's look at a couple examples of that. The one thing you will notice is in this, numbers really don't mean much, because all we need to find is the sign of the infinity. Once we have that, that's all we need, the sign of the infinity. So let's look at a couple examples. limit as x goes to 2 of x minus 3 over x squared minus 2x. Well, the first thing we hope is that we can do a direct substitution and that will work. What happens if we do a direct substitution? Negative 1 over 4 minus 4. 4 minus 4 is 0, so you get negative 1 over 0. So you get a number over 0. Well, that means we're going to check what happens on both sides of 2. Now, to do that, it's most convenient to factor these out entirely. And we'll see why in a moment. So before we check both sides of 2, let's factor that denominator, which we can do by taking out an x. Take out an x from that, you're left with x minus 2. Well, now let's check both sides of 2. So first we'll check, the right side of 2. We know on one side of 2 it's going to be an infinity or a negative infinity, depending on what, if it looks like this, or if it looks like this, or maybe it even looks like that. All we have to do is figure out if on one side we get a positive or a negative infinity. And we're going to introduce some notation to simplify the writing we would have to go through. So this notation is, I've never seen it in a text, but I kind of made it up last year because I thought it simplified these problems a lot. We're looking at the right side of 2. So we're considering numbers slightly larger than 2. We're not considering 2. Numbers slightly larger than 2. Well, what happens if we substitute a number slightly larger than 2 into x minus 3? Slightly larger than 2 minus 3. That brings us to the left of 0. In other words, that brings us to a negative number. Slightly larger than 2 minus 3 is negative. We're going to record that like that. A negative sign, I'll use parentheses, because in general these are multiplied. What happens on the bottom if we take numbers slightly larger than 2? So numbers on the right of 2. Number on the right of 2 substituted here is also, number slightly to the right of 2 substituted here is a positive number, because it's just x. Number to the right of 2 substituted here gives us number to the right of 2 minus 2. That's a positive number. So in general, you should not substitute like 2.1 or 2.01 or something like that. But in your mind, you can think of it like that. Like a 2.1 minus 3 is negative. A 2.1 substituted here, substituted there, is a positive. A 2.1 substituted here is a positive. Now notice in these, I didn't write what the numbers are. The numbers don't matter, because all we're going to do, or all we need to do, is figure out what sign goes on the infinity. And right here we have one negative multiplied by two positives. One negative times two positives gives us a negative. Well, so that tells us on the right of 2 this limit is negative infinity. Well, what happens on the left of 2? Well, let's see. What happens on the left of 2? Well, we know it's going to be a positive or a negative infinity. We just have to figure out the signs. Let's do the same thing. Substitute numbers to the left of 2, meaning numbers like that number. Sort of. Numbers like that number substituted on top, again, give us a negative. Numbers like that number substituted here gives us a positive, because it's a positive number. Numbers like that number substituted here give us a negative number, because we have numbers to the left of 2, and we're removing 2. That brings us to the other side of 0. So now we have 2 negatives and 1 positive. 2 negatives make a positive. And the positive leaves the positive as a positive. Some people write their infinities as sideways 8s. I've never really been all that good at that. I usually write it as 2 circles, and you can see how many times I screwed up writing 2 circles in a clear way. So I'm not that good at that either. But what did we do here? We showed that the limit on the left was different than the limit on the right. When that happens, the limit does not exist. So it doesn't exist since, maybe I'll just throw the word since over here. Since we had different limits on both sides of, in this case, 2. Let's look at another 2 examples. Let's look at this example. Now first you'll notice this is already factored, so we don't have to further factor it. Well, no, that's your second notice, or thing you notice. The first thing you notice is that this is a limit. So you hope you can substitute. It's very nice when you can substitute. Look at the first 2 examples we did after that theorem. That's how nice it is to substitute. Let's try substituting. Here you get negative 3 over 0. That's number over 0. What we do in this case is check both sides of negative 3. So let's do that. We need to check the right side of negative 3. And we need to check the left side of negative 3. Now what does that mean, the right side, the left side of negative 3? Well, sometimes I like to view that as a number line. I mean, actually, when I'm doing these, I always think of them as a number line, even if I don't write them. There's negative 3 on a number line. A number line, of course, is a way of saying x-axis or y-axis. We'll use x-axis since we're doing right and left. Where are we doing right and left? Well, here we want numbers on the right of 3. So on the right of negative 3. The right of negative 3 is over here. So we're considering numbers on the right of negative 3. Numbers like that are on the right of negative 3. Well, there's a negative sign there. Hopefully you can see that. Numbers like that substituted into the top give us a negative. Remember, we have a number over 0 here, and we're checking both sides, so we know it's going to be a positive or negative infinity on both sides. All we need to do is figure out positive or negative, and then analyze. That's the only thing we have on the top. On the bottom, what happens? Well, negative 2.99 here, plus 3, gives us a positive number. Positive number squared is a positive number. So you could write that as positive. You could write that as positive squared. I'm going to write it just as positive. Why am I going to write that just as positive? Why am I going to write that just as positive? Well, it's a shortcut. It's a shortcut. All we care about is the sign. Something squared is always positive. So that we know this denominator is going to be positive no matter what we substitute in. All we can't substitute is negative 3. And since we're taking the limit as x goes to negative 3, that will never be substituted in. So that denominator is always positive. So here we have one negative sign and a positive sign, so that makes a negative infinity. Now what happens on the bottom? Well, we need numbers to the left of negative 3. Numbers like this one. Don't use numbers like that one. That is on the left of negative 3. But we want to remain close to negative 3. Think of numbers like that one. Well, substitute that on top. Again, you get a negative number. On the bottom, you get a positive number. But one step back, if you put this negative 3.01 in the bottom, you get a negative number squared. This number plus 3 is not larger than 0. It stays negative. So you get a negative squared, which is positive. So I'm just going to write that as a positive. Well, I'm going to write that here as a negative squared. But I don't like how that looks. I'd rather just write it as a positive. I mean, having that squared introduces additional numbers. Who wants additional numbers if you don't need additional numbers? Well, I don't. Maybe you do. And given 40 some, however many students, it's quite rare that all of us would agree exactly on the same thing. So I will just leave that as a positive. You might want to use a negative square. But here, what do we have? One negative. So that makes a negative infinity. Now notice what we did here. Limit on the left is negative infinity. Limit on the right is negative infinity. And we will conclude from that that the limit is negative infinity. Let's do one more. Now in these you could be expected to factor like we did in the first one. You could be expected to factor things like x squared minus x minus 6 into what, x minus 2, x minus 3, x plus 2. Sometimes you could be given something in its factored form. So let's do this limit. Limit as x goes to 7 of x plus 3 times x minus 4 times x minus 10 all over. So this is one fraction. I don't like writing on the seams of the chalkboard because they're annoying to erase. All over, let's put a square on something. No, let's put a cube on something. We haven't had a cube. Let's throw a cube on, not that one. That one's not as interesting. Let's throw a cube on both of them, I guess, so I don't have to erase. And let's do on the denominator x minus 5 squared, why not, times x minus 7 fifth times x plus 2. We don't have the plus on the bottom. Let's do this limit. It's a lot of numbers. But you'll notice the actual numbers don't matter much unless it's a 0. When do we get 0? Well, we substitute 7. That's not a 0. 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 But you substitute 7 here, you get a 0. So right here, this is of the form number over 0. Well, that means we check both sides. So let's check both sides. I'm going to call this function f. so I don't have to rewrite it twice. I'm just going to call it f. I'm not going to write down that I'm calling it f. I'm going to just call it f. Equals. What does it equal? Well, this limit is going to be a positive or negative infinity. This limit is going to be a positive or negative infinity. So we just have to figure out which one. Numbers to the right of 7 are numbers like this one. We will try substituting numbers to the right of 7 into this fraction. Numbers to the right of 7 here give you a positive. Numbers to the right of 7 here give you a positive. And we'll take care of the cube. Positive cubed is a positive. Numbers to the right of 7 here give you a negative, because that negative 10 is larger than numbers very close to 7 on the right of 7. So we get like a 7.01 minus 10 is a negative. Negatives cubed are negative. What happens on the bottom? Well, on the bottom, we have x minus 5 squared. I'm not even going to think about that, except to say it's definitely positive. Positive squared, but it's a positive. Here we have x minus 7 to the 5th. A number slightly larger than 7 minus 7 is positive. Positive numbers to the 5th are still positive. Over here, x plus 2. That's not interesting. Let's throw another negative in here. Let's make it negative 20. So if you're taking notes, sorry, you'll have to erase or scribble something out. Because I changed the positive to a negative. Number slightly larger than 7 minus 20 gives you a negative. We know it's going to be an infinity. Now we just have to count the negatives. Two negatives. Two negatives cancel out. So on the right of 7, we have a positive infinity. On the left of 7, that would be numbers like this one. On the left of 7. Substitute that here, you get a positive. Substitute that here, you get a positive. And you cube the positive. Substitute that number here, you get a negative. And you cube the negative. Negatives cubed are negative. Substitute here, you get a positive because it's squared. Substitute here, you get a negative. And then you raise that to the 5th power, which still gives you a negative. Substitute that here, you get a negative. And it's an infinity. Which infinity? Well, there are 3 negatives. It gives you a negative infinity. Because 2 of them will cancel, you're left with another. So on the right of 7, we have a positive infinity. On the left of 7, we have a negative infinity. So this limit does not exist, because those are different infinities. And you can say since that. So all of these 4 cases, the first instinct should be to hope a direct substitution works. On your test, there will probably be one where a direct substitution works. And it might not be immediately obvious at the beginning that it works, but do try direct substitution first all the time.